So let's start with the 4.2 handout on null spaces, column spaces, and linear transformations. We start out with A being an m by n matrix, and we just want to recall the fact that when we assign a vector x to the product ax, which is another column vector, we think of that assignment as a linear transformation that changes x, which is an Rn vector, into ax, which is a vector in Rm. It's good to look at a specific example here where A is a 2 by 3 matrix. If x is a vector in R3, then A times x is a vector in R2. So this matrix multiplication, A times x, represents a linear transformation from R3 to R2. Now, take any m by n matrix A. The null space of A is the set of all solutions x in Rn to the homogeneous equation Ax equals 0, where 0 is in Rm. We're going to denote that NULA and call it null A. Theorem number 2 in this chapter. The null space of a matrix A is a vector subspace of Rn. And it's not too hard to verify properties A, B, and C of the vector subspace definition from 4.1. Since A times 0 equals 0, 0 is in the null space. That's the first property we have to verify. If U and V are in null A, it's not hard to show that the sum of those vectors U plus V must also be in the null space of A. And if C is a scalar, then a scalar times an element of the null space of A is also in the null space of A. So those three properties that have to be verified for a subspace have been verified, and null A is officially a vector subspace. Let's do this exercise. Find an explicit description for null A by listing vectors that span the null space. So for this matrix A is actually a 4 by 5 matrix. What we want to do here to describe null A is to solve the matrix equation Ax equals 0. So I can set up the augmented matrix for that equation just by adding a column of zeros on the end. And by row operations, we can put that matrix in reduced echelon form in a few steps. And here's what the reduced form looks like. And notice that there are 3 pivot columns and 2 columns corresponding to x2 and x5 are not pivots, so x2 and x5 are free variables. And my equations for the general solution are x1 plus x2 plus x5 equals 0 from the first row, x3 plus x5 equals 0 from the second row. The third row gives me x4 equals 0, and the fifth row is just a 0 row, so it corresponds to the equation 0 equals 0. If I write out now my solution, vector x, it will have 5 components, and x1 from the first equation is minus x2 plus x5. x2 is free. x3 from the second equation is equal to negative x5. x4 is always equal to 0, and x5 is free. So I can express this general solution as x2 times the vector negative 1, 1, 0, 0, 0 plus x5 times the vector negative 1, 0, negative 1, 0, positive 1, where x2 and x5 are any real numbers. And now let's be a little fancier about things. We can now say that the null space of that matrix A is the span of these two constant vectors, since it consists of all linear combinations of these two vectors. And there's our description of the null space of A. And we've completed that exercise. Let's move on to the next page of the handout. And here, if A again is an m by n matrix, we're going to define the column space of A to be the span of the columns of A in Rm. We'll denote that COLA. So this is another vector subspace. If A is m by n, then the n columns of A are each m by 1 vectors, and thus are vectors in Rm. Recall that AX can be thought of as a linear combination of the columns of A using the entries of X as weights. That is, if A has columns A1 through AN, then AX is X1A1 all the way down the line to plus XNAN. So theorem 3, let A be an m by n matrix, then column A is a vector subspace of Rm. Proof is actually shorter than the theorem 2 because we can apply theorem 1 from this chapter. Column space is a span, and any span must be a subspace of the vector space it sits within. So column A is a vector subspace of Rm. Little exercise here at the bottom. If let B be a particular vector in Rm not equal to 0, and let A be an m by n matrix, is the set of all solutions X to Ax equals B a subspace of Rn. And well, if it's a subspace, we'd have to check the three properties of subspace, right? And first we want to verify is the zero vector in this set. And if it were, then when we take A times 0, we'd have to get B. But A times 0 is going to be a zero vector, and that is not equal to B because we chose B to not be 0 to begin with. So thus 0 is not in this set, and it's actually a subset of our n vectors, so the set is not a subspace. I thought this was kind of interesting because if B were equal to the zero vector, the set of all solutions to Ax equals 0 is a subspace. That's the null space. But if we choose a non-zero vector, the set of all solutions to this equation Ax equals B is not a subspace. On to the next page. And here's just some pictures to help us kind of keep our feet on the ground with all these subspaces and dimensions that we're talking about. So back to A be m by n. Think of the assignment X to Ax as a linear transformation from Rn is the domain space, to Rm is the codomain space. So the domain dimension always matches the number of columns of the matrix A. The codomain dimension always matches the number of rows of the matrix A. And so if you think of this multiplication by A as a linear transformation from Rn to Rm, it's time now to just realize null space of A is a subspace of the domain of Rn. Column space of A is a subspace of the codomain of Rm. And in fact, column space of A is really just another way to say the range of the linear transformation. It's a set of all images of vectors under that transformation. Now, let's do a little problem here with, let's see, A is a given 3 by 2 matrix, and the question is this vector -3, -4, -11 in the column space of A? So here, just notice A is 3 by 2, so x, that association x to ax, is taking us from R2, x are R2 vectors, to R3, so it makes sense to talk about a 3-component vector possibly being in the column space of the matrix A. What we want to do, if we could call B our -3, -4, -11 vector. We just want to know, does AX equals B have a solution? Solution X, which is a vector in R2. That's the question. And so this just takes us back to our augmented matrix situation in row reduction. So let me copy the columns of A, make an augmented matrix by adding the B as a third column. So we're trying to solve for an x1 and an x2 here, right? Two variables, so components of an R2 vector. That would solve this AX equals B equation. So what do? We row reduce, and it only takes a couple steps to get to 1, 0, 0, 0, 1, 0. -3, -2, 0 is the reduced echelon form for that matrix. And so what we see is, we see that x1 equals -3, x2 equals -2 is a solution. In fact, it's a unique solution to the AX equals B equation. So the answer here to the original question of the problem is yes, our vector -3, -4, -11 is in the column space of the matrix A. Part B is really the same kind of exercise. We're just using a different matrix here. So for part B, we could let our B vector be -3, 2, 10. And again, we have to solve AX equals B. And my augmented matrix would be 1, 2, 3, 0, -1, 1, -3, 2, 10. And it doesn't take long at all to work through the steps to get that reduced to 1, 0, 0, 0, 1, 0, -3, -8, 27, I think I get. And what we see is from that third row that the system is inconsistent. That corresponds to, 0x1 plus 0x2 equals 27, which is impossible. So there's no solution to that matrix equation. And so the answer to part B is no. -3, 2, 10 is not in the column space of the matrix A. And okay, we finished that one. Let's just talk about the last page of this handout. Now, a lot of this might seem like repetition on this page, but all we're doing is we're taking language we used for Rn and Rm spaces, and we're now going to apply that language to abstract vector spaces. So we're going to call V and W any vector spaces, not necessarily Rm or N or N or M. And we're going to define a linear transformation from V to W, from one vector space to another, to be a function with domain V, codomain W, such that T of the sum of two vectors in V is going to be equal to T applied to the first vector plus T applied to the second vector. So the images will be vectors in the space W here. And we also, for a linear transformation, need that the function T applied to a scalar multiple of a vector U in V be equal to that scalar multiple times the T applied to that vector U. So these are the same conditions we use to define a linear transformation from Rn to Rm. Here we're just making a definition for abstract vector spaces. So in the case of an abstract vector space like VW here, we have this idea of linear transformation as a particular kind of function from one to another. We don't necessarily have a matrix to describe it. A couple more vocabulary words. The kernel of T is the set of all U and V such that T of U equals 0 in W. If T is defined by a matrix, then the kernel of T is exactly the same as null space of that matrix. So really for us in this course, kernel, null space mean the same thing basically. We use the word kernel when we don't have a matrix. We use null space when we do have a matrix. And similarly, the range of T is a set of all W and W such that W equals T of U for some U and V. If T is defined by a matrix A, then range of T is exactly the same as column space of A. And in this course, it's okay if we interchange range and column space. In fact, we've already seen that the column space of a matrix is the range of a linear transformation defined by that matrix. And finally, just a couple words, theorem, that if T is a linear transformation from a vector space V to a vector space W, then kernel of T is always a subspace of V, range of T is a subspace of W. It probably feels like we've already stated these or proved these facts before. Here we're just reiterating it in the context of abstract vector spaces, which we will speak about a little bit more as the course goes on. So that's the end of our 4.2.